Last time we started section 3.3 and we had taken a look at the three models for multiplication. And the three that we had encountered were called repeated addition, this idea of something being added together multiple times. The second one was an array model. These are used for sets, so you have whole numbers of objects, and we use this example with cookies. And then we had done a model for multiplication that's called area, which feels a lot like an array model, but it's used for measurements of things instead. So where I want you to start today is I want you and your partner or partners, for those of you who are in groups of three, to create a word problem for each one of these three different models, just like we did when we were doing subtraction last week, okay? So go ahead and take just a few minutes to create 3 word problems. All right, we're going to do some examples. Oh, I don't even mess with that. Do some examples of these, and so I want to hear from each group once. So pick out which one you wanted to share, I guess, basically, or whatever. But I need somebody to share their example for repeated addition. Who would like to share? All right, Kaylee.
If there's 2 sporting events every Saturday for 3 weeks, on the 3rd Saturday, how many games will have been played?
Fabulous. Okay, so something that's happening repeatedly. What else? Another example. I don't even care. Cassidy? All right.
Susan rides the bus to school in the morning. If she rides it 5 times a week for 4 weeks, how many times will she ride the bus?
All right, very good. All right, let's do array. Array is probably my favorite one. Yes?
A teacher rearranges the desks in her classroom. She arranges them in rows of 5 by 4 desks, with 4 desks in each row. How many desks are in the classroom?
Good example of array. Did you guys want to do yours, Tira? Or have either one of you?
Karen's planting flowers. She has enough room for 5 tulips wide and 5 tulips across. How many tulips can she fit in her flower bed?
Fabulous. Okay, those are great examples of array because they're objects that we don't cut into pieces, right? It's not a portion of something. Okay, how about area then? Because it's a similar one. How about area? Do you guys want to do yours?
Jane is measuring in her yard for a pool. If the pool is 10 feet wide and 12 feet long, how much area will it cover?
Very good. So we're talking about the ground area. We want to be careful. I had somebody do a pool problem on one of these once, and it turned into a volume problem really quickly. And I was like, whoa, whoa, whoa.
Yeah,
Slow down.
That's what we were trying to.
Yeah, be careful with the volume on that one. Okay, and who didn't do theirs yet? Right here in the middle. All right. One more.
We have Bobby and Joe are building a tree house. They have space to make it 8 feet wide and 10 feet long. How much area? How much area is the floor of their tree house?
Good. All right, great. So these are good area questions. Some other things that you might not have thought about in terms of array, because I don't know what all of the other of you guys kind of said, but array is something that you probably have seen and you don't even think about it. So think about objects for a moment. What kind of objects do you purchase in arrays? Cookie dough is a good example. The ones that are pre-made cookie dough. Yeah? What else? Cupcakes, right? Cupcakes are a really good example. Yeah. Something else. Did you have one? Donuts. Yeah, donuts in a donut box. Yeah, that's a very good example. How about, I'll give you a couple examples that are non-food that you probably purchase. You guys are all about the food. How about soda pop? I mean, that's sort of like food, but cans of pop? Like, do you guys know what I'm talking about? Right, like 12-pack pop? Okay, good. What's that? Toilet paper, that was my other example. Very good, dear. Toilet paper is a really good example, and that one's definitely not food. All right. Okay, let's take a look at some whole number properties now of multiplication. So we've done some of these properties with addition. Some of them are going to come back again here. And then we've got some new ones in here as well. So the first one up here is closure. That was your favorite one, right? Closure is the idea that if we take 2 items and we combine them with an operation, and now the operation is multiplication, then we still have that same kind of an item. So whole numbers have the ability that when we multiply 2 whole numbers together, we get another whole number. All right? So if we take 5 times 3, we don't get 4.5. Right? So some of you are still working on some example problems with Gauss. Do you guys remember Gauss? Yes? Problem number 1 on your test from repeating test? Gauss? He's the one where we added things together that were in sort of a pattern in some way, that we had this pattern to be able to do this. So a few of you are still working on that example 1 problem, and you're having some problems, and occasionally I get answers where I'm told that the sum, when I add these things together, turns into a multiplication problem, all whole numbers, and then before I know it, I get an answer that has a decimal in it. And so as soon as I see a decimal, I know something went wrong, because I should be able to multiply whole numbers together and get another whole number. I should be able to add whole numbers together and get another whole number. That's the closure property that tells me that, actually. So closure, the idea if I multiply two whole numbers, I get another whole number. All right, commutative. So commutative is this idea of switching orders of things, right? And we've encountered that it works for addition, right? Add two numbers together in either order, we get the same thing. And we encountered that when we do it with subtraction, it didn't work, right? Subtraction didn't have this property. Well, multiplication does as well. When we multiply in either order, 5 times 3 or 3 times 5, both ways I get 15. That's actually something that makes things really nice and simple when kids are learning their multiplication tables and their addition tables. That they don't have that property quite the same way with subtraction, is that we have this ability to reverse the order. So when I worked with my daughter on her multiplication tables, and we had flashcards. Did anybody use flashcards when you were in grade school? We got out flashcards because I'm kind of old school about stuff like that a little bit. And so she had the whole cool stuff on the computer where she could practice and stuff too. We did get the flashcards out. And so the first thing we did is we worked on the twos tables. Do we know how to do all the twos? Then we worked on all the threes and we worked on all the fours. But what continued to happen, Sydney, is like this problem you did up here, is that as I added on another set of tables, I didn't actually have to add every single card because she already knew some of them, right? Because if she had already memorized 3 times 8, and then we got to the multiplication by 8 tables, she didn't have to memorize 8 times 3. She already knew it. That's a commutative property that allows me to do the reverse order. All right, next one is associative. So associative says that when I take the order and I have the order the same, right, A, B, C, that the grouping of the values doesn't make any difference. And this can be very helpful when we're doing multiplication because sometimes it's just flat out easier to multiply A and B together because of the numbers that they are than it is to multiply B and C together or vice versa. So sometimes the ordering of these things is more convenient to be done in a different way. And we'll come across that convenience idea in some of our algorithms later. We've got an identity property here. And go ahead and take your notes and write a big thing above identity. What do you think I'm going to write? What word? Additive is what we did before, so what's this one going to be? Multiplicative. This is my multiplicative identity. And it is different than the additive identity. What was my additive identity element? 0. What is my multiplicative identity element? 1. The number 1 has this wonderful property that when we multiply by it, nothing changes. And you might feel like, well, that's kind of a worthless thing to do. But you guys know from working with like fractions and things like that it's really not all that worthless. It actually doesn't usually look like the number 1. It's just got the same value as the number 1 when we use it. So if we multiply a number by 1, it doesn't change. That's all the multiplicative identity property says. Multiply by it, it doesn't change. All right, we've got a couple of new ones. So this is where things get a little bit more interesting. We've got a 0 property. We talked about this last time when we actually defined multiplication. It's part of the definition of multiplication. A times 0 is the same as 0 times A, so it's commutative. And it equals 0. So multiplying by the number 0 just wipes everything out, okay? And then we have the distributive property, and the distributive property only exists now because we have 2 operations, in particular multiplication with addition or multiplication with subtraction. So the distributive property over addition or subtraction says that if we have A times B plus C or B minus C, that we can do this kind of, and you probably have seen these arrows drawn in some fashion like this, where I multiply the A times the B in the first piece. The sign, whatever it was, stays the same in between. So if it's addition, it's still addition. If it's subtraction, it's still subtraction. And then I multiply the A times the C at the end. And again, you can use that no matter what A, B, and C are. Sometimes it's easier just to add the A and B together and then add the B and C together and then multiply by the A. Occasionally, you're just not able to add B and C together. There's some reason why you can't. So you might remember doing things in algebra where one of them was a variable and the other one was a constant. You had no ability to actually combine them. So the best you could do was just distribute and try to simplify them with something else. So there's those properties and those kind of details as well. All right, so I believe what we're going to do next is do some examples where those properties are happening. All right, so we have 6 of them. I want you to take just, a minute or two, go through these and see if you can identify which property is being used. And then we'll reconvene and we'll make sure that everybody has the same property listed beside their 6 options here. So take just about 2 minutes to fill in what you believe the properties are next to these. All right, you're sitting in groups right now. So just in your groups, turn to the people that are near you. Make sure that we have the same things as you go down, okay? So take a look and check with the person next to you, and then we will talk through, make sure all the groups have the same. Did you and your partners match? Mostly? Okay, good. What did you get for the first one? Which property is that? Good, that's the zero property. How about the second one? So the second one is the commutative property. And you guys are writing out the actual words. I'm abbreviating just so that we can move on with it. But how about the third one, C? Associative property. D. Oh, I even heard the word multiplicative. Wow. Yes, the multiplicative identity property. How about E? That is distributive. Very good. It is distributive over addition. How about F? Because F looks really weird. It is the distributive property. If you were looking at that and you weren't sure, let me just highlight for you kind of why it works or why it's that property. Literally, if you take the 1 plus 2, it's appearing in all those places, right? And what it's actually doing is the 1 plus 2 as a single value is being distributed to the 3 and to the 4. So you have the 1 plus 2 times the 3, and then the 1 plus 2 times the 4. Okay, I know with numbers it looks and feels a little bit awkward to write it that way. You've actually used that probably without realizing it was quite doing that with some algebra stuff in your past. So. All right, division. Division of whole numbers. For any whole numbers, A and B, as long as B is not 0, A divided by B is equal to C. If and only if C is the unique whole number such that B times C equals A. We call A the dividend, we call B the divisor, and we call C the quotient. And let me just identify for you in terms of picture form some of that language, and then also an example of the first sort of bullet point because it feels weird and it's really not all that strange. We'll do 6. So let's say I had 6 divided by 3. Well, 6 divided by 3 is 2. And the reason that it is because 6 is equal to 3 times 2. Or you could say 3 times 2 is equal to 6. This is kind of what we did with addition and subtraction. We figured out how to define and talk about addition, and then we defined subtraction in terms of addition. Same thing for multiplication and division. So if a child has memorized their multiplication table, so to speak, usually the place where they'll start talking about division is to think about, well, how do I get 6 divided by 3? Well, think about it on your multiplication tables. What would I have to multiply 3 by to get 6? Oh, it would be 2. And so you think of it in terms of the multiplication factor, sort of this we'll call it a missing factor approach to doing this division algorithm. We call A the dividend, B the divisor, and C the quotient. So if you think about it in terms of writing division out like this, 6 divided by 3 is equal to 2. This number right here is called the dividend. So the dividend is the number that goes underneath the fraction, or not the fraction, but the division bar. The divisor is the value that you divide by. And then the quotient is the solution. It's the answer that you get out of this. Okay, so that's the language that's being used here. All right, so we have some models, just like we did when we were doing multiplication and addition and subtraction as well. There are several models for division. The first thing that you'll notice in these models, let me just make one comment, is that they vary only slightly. There's only a couple of them actually that are any different in the language that's used to create the problem. The difference is in how you solve the problem, okay? Like the model in which you solve it, okay? The way in which you solve it. So let me give you an example. There's two set partition models. And in particular, I bring this up not because your book does, but because we come back to it again in elementary math 2 or proportional statistical reasoning. We come back to this idea. And so if you haven't taken that already, I want you to be aware of it going into there. Junie has 24 rocks. She wants to give them to 6 of her friends. How many rocks will each friend get? So pause for a moment and consider how that compares to this one over here. Junie has 24 rocks. She bags them together in groups of 6. If she gives one bag to each friend, how many friends will receive a bag of rocks? This is actually worded quite differently. It's the same problem. It's still 24 divided by 6, okay? But it's worded quite differently. So imagine that we have our 24 rocks. So go ahead and draw yourself 24 rocks, okay? I'm going to draw 24 rocks as well. And mine are going to be big black rocks. Well, maybe not big. This is what I meant to do. That's a black rock, okay, by definition, and I need 24 of them. And I've just put them in an array model because I like to organize things, not because they need to be drawn in an array model, okay? So don't think that you had to put them in this particular distribution. It says that she wants to give them to 6 of her friends. How many rocks will each friend get? So literally what she has going on here is she has these 24 rocks sitting here, and she has her 6 friends in front of her. And she may go, in fact, go like, you get 1, you get 1, you get 1, all the way down, and then start over and do it again, right? I mean, she may do something like that, especially if she's concerned as a small child of wanting to make sure that somebody gets their favorite rock or something like this. She might also recognize that this is going to happen more than once. Like, they're not just going to each get 1. They're going to get more than 1. So she might say, I think that you can have, like 3. So why don't you pick 3 and you pick 3. Everybody gets 3, and then we go down the list and we realize, oh, I've still got extras left over. Okay? So something of this nature is what's going on. But what I want is I want to separate my rocks into 6 groups. Right? Because there's 6 friends. So the issue with this particular model is that I'm taking my value, 24, and I'm making 6 groups. So I want 6 groups, and they're all equal. And you can kind of see why my array model works pretty nicely like this, because I happen to actually have them in columns where there are 6 columns at this point, right? And if I didn't have them that way, I could still circle them in such a fashion that I have 6 groups when I'm done. So the issue with this is that I end up with 6 groups of 4 rocks. Now, of course, my answer is they each get 4 rocks. But in order to do that, my Doceri is dragging on my pen every time I write. If I write too fast, it stops working, and then I get weird symbols. So if you see me erasing things, that's actually why. All right, so this set partition model is the idea that I know how many people or how many groups I want them in when I'm done, and I'm taking all of my stuff and putting them into that many groups. So this is similar to what happens when you have somebody numbering you off in class, and they say, I want 6 groups. We're going to count to 6, and we start with Kaylee, and you're going to say, we're going to go around the room until we get to 6, and once you get to the number 7, that person is the group 1 again. All right, so I've controlled the number of groups that I have when I'm done by doing it that way. The opposite of that, or not the opposite, but the variation of that, is this example. We have 24 rocks, and she bags them together in groups of 6. So in this model, instead, I still have my 24 rocks, but what I'm controlling in this particular model is not the number of groups that I get. What am I controlling? How many rocks are in each group? So I go through, and in some fashion I circle groups of 4, because I want 4 items in each group. Oh, I'm sorry. We wanted groups of 6 this time. How about this way then? Groups of 6, thank you. We have our groups of 6, and in some fashion we circle 6 in each group. And we end up controlling the number that are in each group now instead of controlling the number of groups. So this is what I do when I say, I want you in groups of 2 or 3, right? I don't necessarily care how many groups I have when I'm done. I want to control the size of my groups. And that's what I do when I do this particular kind of a grouping of models. So of course my answer then, and this one is 4 again, but it's for what? 4 groups. In this case it's 4 friends because she's giving her rocks to 4 friends. Okay, if you guys will give me just one more minute, I can show you the other 2 models really quickly because they're very quick. They don't involve pictures at all. The next one, the missing factors model, is very similar to the way we define division. So this is the idea that I'm going to take 24, and the question is, what would I need to divide by? 24 divided by what? Yeah, equals the 6th. And the question is, how many would I need to divide by to make that happen? Well, it's division by 4. It's my missing factor. All right? So I have 24 rocks. It's the same word problem, 24 rocks. She wants to give them to 6 of her friends. How many rocks will each of them get? The idea is 6 times what would equal 24. It's a missing factor in terms of multiplication. And repeated subtraction, the next one, is actually also very reasonable. This is my idea that what I would actually do with the child, where I says, everybody pick 1. And so once everybody's picked 1, there are 6 fewer rocks than there were the first time. So I subtract off 6 of them. And then everybody picks 1 again. So there are 6 fewer rocks than there were the first time. And I'm left with 12. And then everybody chooses again, and there's 6 fewer rocks. And we do this until we get down to at least not enough that everybody can have 1 left. So we might not get to 0 when we're done. We might end up with a remainder of 2. There's 2 extra rocks left over or something like that. But they can't equally split them. And then the answer is, how many times did I actually subtract 6? And if you count them up, I subtracted 6 4 times. So each kid, or each friend, got 4 rocks. And that's viewing them as a repeated amount of subtraction.